Okay. While that's going around, we'll finish up the handout here. We'll get started here. We did that up there. Here, which is most stable? These two constitutional isomers. 2-butene, 1-butene. Which one's most stable? To answer that, we're actually going to skip that. Let's go down here and ask the same question. Down here we have 4 different compounds. 1, 2, 3, 4, 5, 6. Those are all isomers. I think they're all the same formula. 4 different constitutional isomers. Which one's most stable?
What would be like stable?
Which one has the most potential energy? Which one sits? Taylor?
I think I know the one up there with the 2 choices. I think it's the one on the left.
One on the left. Why is it one on the left?
Because I just read something about the connectivity to the carbons. Like the more it's connected, the more stable it is.
Yes, take home message here, and we'll explain it down here with this table, is when you have alkenes, especially isomers, so we can compare the same number of carbons, the more substituted the double bond, the more stable it's going to be. Okay? So here, we call this over here a disubstituted alkene. That alkene has 2 substituents. Okay, the alkene is here, it has a methyl and a methyl. This alkene is a monosubstituted. It only has 1 substituent. It's got that ethyl group on it. Okay? The more carbon substituents on your alkene carbons, the more stable it is. Why? Let's look down here. The same as here. Okay? Which one of these 4 is most stable thus?
The right one on the right.
The one on the far right, most stable. Because it has 4 methyl groups. Where this one only has 1 butyl. But the butyl is just 1 substituent coming off the alkene. Yes, that's the most stable. Lowest in energy. Why does that matter? Well, for example, if you burn these, which one would give the most energy? If you burned it. Not that one, because that one contains the least energy. Which one's the least stable? Actually, that one. So if you had the same, if you had 1 kilogram of each of these and you wanted to burn it and get the most energy, which one would you choose to burn to get the most energy? That one. Because when it's burned, it'll give off the most, because it contains the most. So that's why we would want to make such. Okay, why is that? It all happens to do with the types of carbon-carbon bonds are there. The carbon-carbon bonds, not the CHs, carbon-carbon. If we look at this stable guy, what type of carbon-carbon bonds are there? It has 1 sp2, sp2. That's the sigma bond here. We're going down here for this compound. Then it has 4 of these, because it has 4 of these right here. They're all the same. Boom. Okay. That's sp2, sp3. sp2, sp3, sp2, sp3. It has 4 of those. And it has none of these. Well, that's the stronger bond. It's the orbitals closer to the nucleus. Okay? If we go over here, this guy, well, every one of them has 1 sigma bond in here, which is sp2, sp2. So that's the same. But when we go over here, this guy only has 3 of these. Boom, boom, and boom, using the sp2. And then the 4th one is actually one of these. sp3, sp3. So you see, this guy has 4 of the stronger bonds. This one has 3 of the stronger, and then it has 1 of the weaker. And as you go across, it gets worse. Because this guy has 1 of the sp2, sp2, and it only has 1 of the sp2, sp3, and then the rest are sp3, sp3, which is the weakest. This guy has the strongest carbon-carbon bonds. Stronger bonds, more stable. And it adds up to being ultimately most stable. Take home, the more substituted your alkene is with carbon substituents, the more stable it is. And it's most clear when you're doing isomers, like in that example. So, we answer which is most stable. We can ask other questions. Of these four down here, which one has the lowest heat of formation? Well, what's a heat of formation? Heat of formation is forming the compound from the elements, carbon and hydrogen. The lowest heat of formation. Okay, think about it. Which one is it? Is it the most stable or the least stable?
You got to add more energy to make it least stable.
What are we looking for? Least stable? Yes, we're looking for the least stable.
No, I'm sorry, most.
The most stable.
It's less energy.
The least in energy. The most stable. Because if you want to make a highly unstable compound, you're going to have to put a lot of energy into it to make it. We're not saying, this is the least energy to make it. Does that make sense? Which compound takes the least energy to make it? That's what this is asking here. The most stable. So it's the same one. Most stable and the lowest HF is the same answer. It's the one to the far right. Okay, then I already got you this here. Which one gives off most heat when burned? The most stable or least? The least stable. Least stable means it has the most energy. So when you burn it, and all these go to CO2, exothermic, which one gives off the most energy? The one that contained the most to begin with, which is the least stable. Make sense? Okay? A little thermodynamics, but qualitative. Okay, just assessing it based on structure, bonding strength. A couple miscellaneous things here. Anybody familiar with saturated fats?
Yes.
Okay, here's some, this is a saturated fat up here, very top. Now it's not fully saturated because that's not saturated. But the side chain is totally saturated. Now why do we call it fat? Because it's just hydrocarbon. And that's sort of term for fatty, or lipophilic, lipid-like, lipid-loving. All right, this guy has this point of unsaturation, so this is an unsaturated fat. And since it only has one double bond, it's called a monounsaturated fat. Okay? And then this down here starts being a polyunsaturated because it gets more than one. Now, we can ask some questions here. Saturated fats, why are they bad for you? Because they're solids, even in your body. And since they're solid, they tend to want to form solids in your blood vessels and form plaque and stuff. Okay? Clog it up. You'd rather have oils that remain liquids and free-flowing that don't clog up, right? Okay? Well, when you put double bonds in these, what does it do to the melting point? It lowers it. See, that guy up there, melting point is 69. It's a solid at room temperature. It's actually a solid in your body at that temperature, unless it's dissolved. These are liquids at room temperature. Okay? Why does the double bond make the boiling point lower? Well, that's easy, because it lowers the IMFs, right? Then the question becomes, why is the IMFs lower? Because this puts a kink into the chain. And it essentially increases the surface area. Well, no, that doesn't work. That goes the other way. Why does the kink in the chain make the boiling point lower?
They can't pack as tightly together.
Somebody's got it.
They can't pack as tightly together.
It can't pack as well together. Okay? Because this van der Waals things, I mean, we assume that the molecules can come together and do the van der Waals if they, okay? But what's easier to come together? Arms that are just stacked on top of each other? Or what if I have something like this? Well, I can't, the more branching, this kink doesn't let the molecules come together and stack on each other and really get that van der Waals interaction. The more kinks you put in it, well, it really affects it a little bit. But basically, you want your fatty acids to have a little kink to them. Okay? Now, trans fats, why are they bad? Because what type of double bonds it is? Is that a cis or trans? Cis. Cis. You see all these cis? Those are all cis double bonds. Those put the most kink. If you put a trans in there, see, that's trans.
Then you can still stop.
You can put trans double bonds in there, and it still remains very linear with the zigzag. But when you put cis, it really kinks it. So even this one down here, it does have one cis. And you could maybe argue, why is that with one cis higher than the other one? That's a different argument we're not going to make. But this would be a trans fatty acid. Most of your trans fatty acids actually have higher melting points. Now I'm going to explain beyond why, even though it has a cis double bond in there. In the end, this is just a little bit of relevant stuff, so when you hear unsaturated fats and trans fats, you kind of see how this applies. Okay? What's next? A couple miscellaneous things. This is a drug given for insomnia. It's actually given as two different stereoisomers. Both of these are given in the pill or whatever. You see the difference is here the alkene, the amine group is on the side of oxygen, but here the amine group is on the side opposite the oxygen. Okay? And since that double bond can't rotate, you can't spin this over here. These are indeed stereoisomers, and what you can do is identify these as E or Z. Do this on your own. Now the compound on the back is very similar, except it has this carboxylic acid group. But this drug is used as a treat allergies, and it's given as only one stereoisomer. And you can again determine that one. Some compounds are given as mixture of stereoisomers, like ibuprofen. You take both when you take it. But some are only given as one. Like tamoxifen, that's just one stereoisomer. And right now we're just talking about alkene stereoisomers. There's another little thing, miscellaneous thing, refrigerants. If you want to read about that, some alkenes here. Things like Freon, but other newer refrigerants that have alkene structures. Any questions about that handout?
You say Creon had an alkene?
No, I don't think Freon does, but there's other more recent refrigerants that are replacing Freon. That article sort of talks about some of those. But it shows a couple structures with some alkenes. It even names them. You can look at the name and see if that name looks right according to how we name things. Okay? Again, I just usually give you a little relevancy, show you the application. Hopefully we're not learning this stuff just to take tests. We're learning this stuff so you can go out and be a well-informed young scientist and go do greater things. Build. Okay, here's a warm-up. Hopefully you spend some time on this. At this point we're going to be moving on to reactions. I gave you the wrong handout today. Wrong handout. White one. White handout. We need to do thermodynamics. Dang it. Addition of HX. Did I get one of those? Oh, there's Yeah, there's supposed to be another handout in between this one. We're going to do it here. The other handout is on thermodynamics. I realized I didn't have that to you yet. It's mainly a lot of review. We will cover it. When we talk about that stuff here, we'll have to talk about it sort of fresh. Okay? But in the end, the quicker we can start these reactions, the better. Okay? So starting tomorrow, we'll start them today. When's the next test? Monday after? Good. Should be back from Chicago by then. Boom. Okay, y'all ready for reactions? So step it up a notch. Okay? Yellow is also our outline. And we'll start with the yellow overview, right here. Alkene reactions. This happens to be an alkene in a ring, it doesn't matter. Alkanes don't have much reactivity. We said we can burn them and do radical bromination. Okay. When we move to alkenes, we have the pi bond. The pi bond is a site of reactivity. Those electrons are held loosely. Those are in a pi bond, p orbitals. These electrons can act as a nucleophile. What does nucleophile mean? They love the nucleus. What's the charge of a nucleus? Positive. They love a positive charge. That makes sense. Electrons like positives. Okay? That's just terminology. We've got to know terminology. The first, nucleophiles react with electrophiles. What does an electrophile love? Electrons. Okay? So the thing, this is your electrons here. And the thing that it reacts with apparently loves electrons, or it wouldn't be reacting with it. So it's called the electrophile. This thing is going to be called the nucleophile, the thing with the electrons. Because electrons like positive, we found the positive in the nucleus. Okay? The first electrophile we're going to react with is H+. And what we're going to see is H plus X minus. This is basically like HBr, HX. Okay? It's ionized. Alkenes react with HBr, HI, to give alkyl halides. Alright? I don't think there's anything to write down here. We're just going to sort of overview here. Alkenes react with H plus and water to give alcohols. Alkenes react with H plus and alcohols to give ethers. These are all addition reactions. These are all called electrophilic additions. In going from here to this molecule, we have added HX. What have we added? Obviously there's an X here, X is halogen, Br is there. So we've added a Br there. What have we added here? How many H's there? One. How many H's now there? Now two. So what is new? Does everybody agree that we have added the H and the X? That's new to the molecule. Because of that, we call this an addition reaction. We added something. There's only like 5 types of reactions in chemistry. Addition. There's elimination. When we went from here to here, did we eliminate something? No, we added an H and a Br. We added HBr in the form of H plus Br minus. Covalent or ionized. Okay? We got to make sure you know where the H's are. I see it all the time. Students do reactions, end up with, don't know how many H's you got there. 1 H here, 2 there. What have we added down here? What's new? There's an OH on the top carbon, that's new. The methyl's still there. What's new down here? Well, there's 2 H's there, so what's new? An H and OH. And if you clump those together, what is H and OH? H2O. Okay? We've added water. When you add water, what do you want to call the reaction? It's a hydration reaction. Okay? I'm giving you some broad introduction here. These two reactions, the H plus is catalyst. Up here, the H plus is not a catalyst.
So these generally going to be endothermic reactions?
That would have been that handout we don't have today. Okay? That's a good question. Let's assess. We can do it. On the handout, we're going to bring, okay, here you go. Tomorrow, bring your calculator. It's your one chance to use your calculator in this class. We'll do it tomorrow. All right? After you get to do simple addition, you might not need it. Let's assess it qualitatively. What's the difference in the bonds we've made here? I see a pi bond here. Is it still over there? Pi bond's been broken. Okay? What's new? That's the only thing that's been broken. Any other bonds been broken here when we got over there? No. What's new? Bond to X and bond to H. Are those, what type of bonds are those? Sigma. We broke a pi and made 2 sigma. Are we getting more stable or less stable? Shayna? Shayna. Where's Shayna? Is it Shayna or Shayna? Shayna. We're getting more stable or less stable? Which is more stable? Pi bond or 2 sigmas? Sigma bond is more stable than pi, right? Sigma's head-to-head using hybrids. Pi bond is weak side-to-side using higher energy p orbital. Sigma bond more stable? Okay, which is more stable? Molecule with a pi bond or one that has 2 sigmas? Yeah, we're getting more stable. More stable means higher energy or lower energy? It's a lower energy molecule. So this is higher energy molecule. If this is higher energy and this is now lower energy, where's the other energy? It's released. So what's the answer? It's going to be exothermic. You see how we did that? We assessed it based on structure.
How does that like reconcile with the SP2 having a more S character, more stability than that having those shorter bonds and more S character closer to the nucleus? Is that just the other one?
The sigma bond here is stronger. The sigma bond between the carbons is now weaker.
Okay, so it does.
But what we just did gives you your answer. You could argue, or you could ask for an explanation of why the other doesn't work, or account for the answer, or influence the answer. Okay. Those are reactions. Now, up top, in all 3 of these reactions, the electrophile is H plus. H plus, H plus, H plus. What I say in the heading? Reactions with H plus. Okay? Down below, the reactions will be other electrophiles. Okay? Lots of reactions to learn. The first reactions we'll look at is reacting with H plus. And we'll do these in sort of order as I showed them. The first one's going to be reacting with HX. And if we look on our outline, that's indeed what I say. Remember number 1, addition of HX to give what? Alkyl halide. That's what we showed. Whenever you add HX, it's called a hydrohalogenation because you're adding hydrogen and halogen. Terminology. We're doing a hydrohalogenation reaction, also known as addition of HX. These are things we will cover. Okay? I'm not going to refer to this outline, but ultimately that's what I'm following. Keep it handy. I'll be looking at it to make sure I'm hitting what I need to be hitting. We're going to be mainly over here. All right? So addition of HX. Here we go. Here's just another repeat of the reaction. We take this alkene, react with HBr, we get this product. It's an addition reaction. There's the Br. Where's the new H? There's 2 on this carbon. Now there's how many on the carbon? 3. You see, there's a new H there. You see, the H and the Br. We say that the H and the Br have been added across the pi bond. Because one is here and one's here. Okay? Now you've got to just know where that H is. Sometimes I will show it in and say, here's the new one. Please don't think that there's not 2 others there. Okay? But I just drew in the new one. Now sometimes I won't draw it in, and I'll say, there's your product. But all the times I see students look at it like, we just added the Br. No, we also added an H. It's there. You see it? You've got to know that. Got to keep track of Jason. If you want to draw them in, draw them in. It's not illegal to draw them in. Okay. Mechanism. Now the mechanism we will do. Learning mechanisms is part of organic chemistry. What is the mechanism? Using arrows to show all electron movement. Show movement of electrons, not movement of atoms. Movement of electrons. Now on the warm-up, there's a nice mechanism for you to try right here at the bottom. It might look very complicated, but when you do this warm-up mechanism, anybody done it already? Give it a try. What are you going to do? Send it to the test today? Please do this mechanism this afternoon, tonight. Okay? You want to show what electrons are doing. Okay? Now here's the result. And we're using cesium fluoride. Now, if we look over here, there's obviously an F bonded to silicon. Now this is ionic, right? We took Gen Chem. This is cesium plus F minus. F minus has 4 lone pairs, and it's a minus. And if you look over there, the fluorine is now bonded to the silicon. So, obviously the fluorine is bonded to the silicon. How do you want to show that happening? Typically, your reactive electrons are either lone pairs, that's the most common, or pi bonds. Pi bonds is what we're about to do the mechanism of. Okay? Now your first step would be this making a bond to silicon. But obviously that bond has to break, SiO, because there's no SiO bond anymore. And so these 2 electrons have to be moved where? Either onto the silicon or the oxygen. But if they're moved onto the silicon, what, as a lone pair? Well, if you do a Lewis structure, the silicon doesn't have a lone pair. So they need to be moved on to where? Actually, the oxygen. Basically, you just see where the electrons need to move, and you do it with your arrows. And when I give you a mechanism question, products will be given. I'm not asking you to predict the products. I'm asking you to show the arrows with the electron movement. So give that a try, and of course we'll do plenty of this. that should really all just fall into place like dominoes. Just move your electrons where you need to be, and at the end, you should have 4 individual structures with correct Lewis structures, with lone pairs where they need to be and stuff. Okay? That's sort of an intro. So here we go. Let's do mechanism. How does this addition reaction take place? Well, pi bond is a source of electrons. I already said that. Now the HBr can either be shown ionic or covalent. Here I'm showing it covalent, but with a dipole, because we know it has a dipole and the H is partial plus. So working with covalent, partial plus. These are electrons. What are electrons like? They would like some partial plus. So these electrons are attracted to this partial plus. And what I'm showing here is these electrons will move and make bond to H. Now the H can only have one bond. So when it makes bond to H, these electrons get pushed onto bromine. Well, bromine would love to have those electrons because it's kind of greedy, right? And when the electrons move on to bromine, the HBr bond is broken. Bromine gets an extra lone pair. It becomes Br minus with 4 lone pairs. And now we have a bond to H. Down here I'm showing it where I ionize the HBr first and the electrons just attack the H+. Your Br was already formed in the ionization. Now, it may be a touch difficult to envision these electrons. I'm going to do it with my arms here. Actually, I wish one day we would do some like dance or something and have dancers doing electron movement. Here's pi bond here, okay? See it? One carbon here, and I'm the other carbon, okay? And you're the HBr. Y'all be covalent. So you're Br, Sarah. And hold her hand. But you got to be pulling hard because you see, okay. So you're pulling it, and so you're left with some partial plus. And I'm walking down the road here, and these electrons, and I start being attracted, but I'm going to break away, and I'm going to go bond. And when I bond, you have to just yank her electrons off.
Okay.
So I bond to you, you take the lone pair, okay? So I bond to you, and you take the lone pair. And when I bond to you, we now have a carbonate sigma bond made. Again, how do you make that bond? That's that book that thick, and we're not getting into that precise. But we got to look back over here. This carbon no longer has a bond. So it only has 3 bonds. So it has a charge, and it's a positive charge. Okay? Because see this carbon out here? It has 2 bonds and 2 more. But when these break away from that carbon and go make a bond to H, this carbon now only has 3 bonds, 1 less bond. That carbon is now plus charge. And so we're left with this, and we call a carbo plus charge a carbocation intermediate. And then there's that Br minus that got formed. We've got a couple of questions. Your Tom, go ahead.
Why is the hydrogen more attracted to the less substituted carbon?
We'll get to that point. Very good. We'll get to that question.
And that's why I wanted to think that's just the carbon.
Good. That you do have a choice. In my demo, I couldn't do it any other way because I can't break this arm away. But with the pi bonds, it could do either way. It could really hinge either way. We'll get to that. The answer will be hopefully very clear. This is an intermediate. Okay, an intermediate is something that's very discrete. We can observe it. It's a carbocation intermediate. But that's not the final product. How can we get the final product? We can propose as a mechanism the Br minus electrons then make a bond to the carbocation because electrons like positive. And even though this Br is greedy and it likes being minus, this will still happen because a covalent bond is good and you'll get your end product. So how many steps in this mechanism? This is step 1 and this is step 2. Each step in your mind says, well, what happened in step 1? The alkene attacked the H+. You can show it either covalent or ionically, but both of these are considered H+. Okay, that's step 1. And you form what intermediate? Carbocation. What happened in the second step? The Br minus then turned around and made a sigma bond to the carbocation, and that gives you your final product. Two-step mechanism. Okay, when we have two steps, we can say, which one's the rate determining step? Well, let's graph this. And this is where I would have covered this on the other handout. Reaction coordinate diagram. A reaction coordinate diagram is where you show the energy flow of the reaction. Where some just energy, and this is going to be called reaction progress. And we're going to start out by showing just energy of the starting material. Here's the energy level, that's just what the level is. There's your starting. Final product. Let's put it up here. Higher or lower? We've already answered this. It's going to be lower. That's going to be your product. How many intermediates do we form in this mechanism? One, carbocation. How's it going to sit compared to the starting? Carbocation is charged. Since it's charged, it's going to be higher in energy. So I'm going to put it kind of up here. And this is our carbocation. Okay? By the way, is that a primary, secondary, or tertiary carbocation? Is it positive on a what type of carbon? Yeah. Tertiary carbocation. Okay. One intermediate, starting, one intermediate product. Okay. When the reaction takes place, do we go like straight there in terms of energy? No. We have what? We have activation energy leading to the formation of that intermediate. And the activation energy is we're going to get something that looks like this. Okay? Where this here is called what? E sub A, your activation energy. And what does this look like right here? Or what can we call this at this point? What is the molecule, or what's happening right here?
Transition state.
Somebody said it.
Transition state.
Transition state. Now that's the ultimate hot. What is a transition state? It's like bonding man, okay? When the bond is being made, it's that bond making process that it's hard to see, okay? But there's got to be some intermediate process where this is being made, that's being broken. But that's actually higher energy than when you fall into this well, and when you get to this here. See, this is an energy well. Okay. From there, now we're going to have that bromine come in and making that bond. But that's a transition state. That bond's being made. Now, from here we're going back downhill to a neutral molecule. Is this transition state going to be high or fairly low? Low. Why low? Because if you're making something that's high in energy, you said you're going to take a lot of work to make it. Okay? But if you're making something that's lower in energy, it doesn't take much work to make it. We're falling downhill. Zach? Does it take much energy to fall downhill?
No.
Go to the top of the stairs. How much energy does it take to fall down the stairs? All you got to do is bend your legs and just lean a little bit, and you're going to go. Okay? All you got to do is just get a little bit of energy, and you're coming down. That's not going to be that high. There's your reaction coordinate diagram showing how many transition states do we have? Two. How many intermediates do we have? It sits at like a well, energy well. One. Two steps. Which is going to be the rate determining step? The rate determining step is your hardest step. The first one. Ultimately, see, it's the one with the highest transition state energy. Okay? First one. First one's your rate determining step. We call this step over here fast. Rate will depend on this first step. So if you wanted to speed this reaction up, which step would you focus on? First step. Speeding up the fast step ain't going to matter. Your bottleneck is at the first step. You're wasting your time speeding up the fast step. Right? Okay. Questions on the right. Is this reaction thermodynamically favored?
Yes.
Yeah, we kind of answered that at the very beginning. It's going to be exothermic. Okay? Ultimately, we're sitting lower in energy than where we started, exothermic. That's thermodynamically favored. Rate determining step, we identified that. Is this reaction kinetically favored? Assess it up here. Is it kinetically favored?
That looks all like thermodynamic.
Y'all think about it. Let's look at this here. Why not do this reaction the other way? And a couple of questions alluded to this. Why do we do this reaction and why did I erase it? Wish I didn't erase it. Keep yours right there. Why did we not do this way? First off, what would be the mechanism here? It looks like here, where's the new H? New H is here. So if we show the mechanism here, I'm going to show this ionic. We would show the electrons breaking away from that carbon and sort of hinging like this. Okay? Now when you show this, sometimes the book will just do like this. I want you to do it like this. Because if you do it the way I'm going to show you, you'll remember it easier and you'll do better on everything. Hinge it. Yank these electrons away from that carbon, okay? And take them and go bond to that H. So take this and yank it, okay? Envision what your arrow means. Yanking this here. Now what do we have? We have boom, boom. There's that carbon. I'm going to draw this like this. But see, I yanked these electrons away, and I went and bonded to the H. And now that carbon has only 3 bonds. It's got 2 H's. Right? You want me to draw them all in? But it's only got 3 bonds. So what is this? Positive. Of course it's a positive. Because if a neutral reacts with a positive, you've got to have a positive. So that's there. Can I erase these H's because they look odd if you. They're there, right? What's the next step? Carbocation intermediate, then we be our minus with attack. Okay? Why does it not happen this way? These electrons make bond. What type of cation is this? Primary, secondary, tertiary? Primary cation. Which is more stable? Primary or tertiary? Why is tertiary more stable? Up there, I erased it. What did there look like? This. What do we have here? We have alkyl over here, and alkyl inductively donates, right? sp3 carbon donates. We talked about it in context of acid-base chemistry. That doesn't mean we can't talk about it here. sp3 carbon donates. Well, this guy has 3 donating. more sp3 carbon, inductive donation, more stable. Wish I hadn't erased it. On your diagram, where would this carbocation fit? I'll try to redraw it real quick. Didn't we have boom, boom, boom? And this was that one? Starting, okay. Where would that carbocation, the primary one, go? Would it be lower or higher? Be higher, it's less stable. It'd be up here. Okay, this would be up here. Not as stable. So when this reaction takes place, we can either go this way or we can go that way. Now, like water running down the road. When water runs down the road and it comes to a fork and this one goes up the hill, this one goes down, or whatever, which way is nature going to prefer? Nature prefers the lowest energy pathway. So it's coming in, it takes this pathway and it forms what? The tertiary carbocation. And from there you end up with the bromine on the tertiary, which was the top product. It's not going to give this carbocation. At least not predominantly. Okay. Please be doing some reading. Please answer questions on the side. Please look ahead. You've got to do some reading and come with questions. We'll have thermodynamic handout tomorrow. We'll hit that pretty quickly because it's going to be mostly review. Please do the warm-up page. And please be doing problems in your textbook. Alkene Reactions. Okay guys, see you in the morning.